the lesson video for section 20.3 in physical science, and as always, if you subscribe to my channel, you'll have all my videos for the whole year. So we're going to talk about circuits in this section. So an electric circuit is the complete path through which charge can flow. So remember, if there's any break in the path, then the current cannot flow through it. It has to have a complete path. So circuit diagrams use symbols to represent parts of the circuit, including a source of electrical energy, like a battery or something like that, and devices that are run by the electrical energy. So for example, like light bulbs, things like those. So here's just an example of a circuit diagram. And so if you look, here is our source right here, and then these are different resistors. And so you can see we have that complete pathway that the electrons can flow through. So switches show places where the circuit can be opened. If the switch is open, the circuit is not a complete loop and the current stops. This is called an open circuit. So a switch, it usually looks like this, like you'll have a little line and it can look like this or like this. So if it's open, there is no complete path. If it's closed, there is a complete path. So when the switch is closed, the circuit is complete and the charge can flow. This is called a closed circuit. So think about an on-off switch. If the switch is on, then you have a closed circuit, so electricity can flow through.
Coach Technic, please stop by the counseling office. Coach Technic, please stop by the counseling office.
There we go. All right, and then if your switch is off, it's an open circuit, and so in that case, the electrons cannot flow, or electricity cannot flow through. So this would be an example of each. So this one is open, so you can see that you can't have electricity flow through, so your light bulb is off. And here your switch is closed, so we have that complete pathway, and so in that case, our light bulb is lit. The positive and negative on the battery symbol indicate the positive and negative terminals. So if you ever looked at a battery and you see the little plus and minus, it's represented by that same notation on a circuit diagram. So a wire is just a straight line. A resistor is usually drawn as a zigzag line. A light bulb, sometimes you'll see an actual light bulb, sometimes you'll see a circle with an X. Your battery is represented by a larger line and a smaller line. And the important thing to remember is this is not a break in the wire. Okay, so this is where your battery is. So if you see this, I don't want you to think that means it's an open circuit. A fuse is just represented by a rectangle, and then a switch is represented as two dots with your line. And so again, if your line connects the two dots, it's closed and your devices will work. If the line does not connect to the other dot, then it's open, and whatever devices you have will be off. So there's different types of circuits. We're going to talk about series and parallel. So in a series circuit, charge has only one path through which it can flow. So if one element stops functioning in a series circuit, none of the elements can operate. The more bulbs you have, the less brightly they shine. So in a series circuit, because there's only one path, if something goes out, so think about Christmas tree lights. If one light goes out, that path is broken. So none of them can come on at that point. All right, and then the more bulbs you have, the less brightly they shine because they're all sharing that same loop of current. So this is an example of a series circuit. So if you look, we literally have one pathway through which it can flow. And so here we have three light bulbs, so if one light bulb blows, all three of them will be out. All right, and then if I only had two light bulbs, they'll glow brighter than three light bulbs together. And here's just a circuit diagram example of it instead of drawing it with actual pictures. But here we have resistors instead. And so again, we have the one pathway through which it can flow. And so if one of our elements stops working, then all of them will stop. So a parallel circuit, on the other hand, is an electric circuit with two or more paths through which charges can flow. So since there's multiple pathways, if one element stops functioning, the rest can still operate. So a lot of Christmas lights, they're actually a combination of series and parallel. And so what will happen now is instead of if one goes out, the whole string goes out, what you'll find nowadays is if one goes out, a portion will go out, but the other ones will still stay lit. So the other ones that will stay lit are on a different pathway for that current to flow. So this would be an example. So if you look, we have this pathway right here, we have this pathway right here, and we have this one right here. So if this middle bulb stops working, we can still have current flow through here. We can still have current flow all the way to the bottom, so the other two will stay lit. And the same thing, this is just an example of a circuit diagram drawing instead. And so again, if one thing stops working, we still have other pathways that those electrons can flow. the rate at which electrical energy is converted to another form of energy is called electric power. So we've talked about power before. Power that we've discussed before was how fast you can do work. Well, in electric power, we're talking about how fast can we convert electrical energy into something else. So the unit of power is the same that we learned before. It is watt, or capital W, because it is a joule per second. Electric power can be calculated by multiplying voltage by current. So if you remember from the previous video, voltage is represented by V, and current is represented by I, but the units are amps or ampere, which is represented by capital A. So power is current times voltage. And so here's just your units again. So power is watts, current is amps, and voltage is V, volts. Again, with the font that is on this PowerPoint, this is not a lowercase l, it is a capital I. So just make sure you do realize that current is represented by capital I, not lowercase l. Not that either letter makes sense for the word current. So let's look at some examples, as we always do when we have some math. So it says, an electric oven is connected to a 240 volt line. So there's my V. And it uses 34 amps of current. So there's my I. What is the power used by the oven? So I'm looking for power. So remember, my formula is power equals current times voltage. So my current's 34, my voltage is 240 volts. So I do 34 times 240, and I get 8,200 watts. Now this number, I did round on it. When I put it in the calculator, I get 8,160 watts. This is just rounding using something called significant figures, but you don't need to worry about those. If you put 8,160 watts, that's fine. But don't forget those units. That's not fine if you forget units. Or put the wrong ones. Just saying. I like units to be correct. Alright, so hopefully you'll find that in physical science we've been doing a lot of formulas and they all kind of work the same way. So hopefully you're getting used to them. Okay, so maybe pause the video, try these on your own, and we'll look at them together. So it says a clothes dryer uses about 27 amps of current. So there's my I. From a 240 volt line. So there's my voltage. How much power does it use? So I'm looking for P again. So power is current times voltage. I'm looking for power, so I just plug in. So my current is 27 amps. My voltage is 240 volts. I don't know why I just wrote amps out. I can clearly just use the abbreviation of A. Alright, and so then once I do 27 times 240, I got 6,480, and my unit for power is watts. I will go ahead and tell you, it's really hard to figure out how the units convert into one another because they're all multiple units together at this point. So the best thing to do is just remember, power is watts, current is amps, and voltage is volts. You maybe just memorize which is which, and that might help you a little bit. And by the way, this is an I. I realize it kind of looks like a T that's been underlined. That's an I. Alright, so if you didn't try the first one on your own, try the second one, pause it, try it, and we'll look at it together. So it says a camcorder has a power rating of 2.3 watts. So there's my power. If the output voltage from its battery is 7.2 volts, so there's my voltage, what current does it use? So I'm actually looking for I this time. So we're going to have to rearrange that formula, but that's okay. We're getting used to that. So P equals I times V. I'm solving for I. So I have to get I by itself. So how do we get V onto the other side? Well, we do the opposite. Right now, they are being multiplied together. So what's the opposite of multiplying? Dividing. So I divide both sides by V. So I equals P divided by V. And then I just plug in. So my power is 2.3 watts. My voltage is 7.2 volts. And so once I do 2.3 divided by 7.2, I got 0.32. And then my unit for current is amps, or ampere, which is just capital A. Alright, so hopefully you at least got one of those right. This one was a little trickier because you did have to rearrange, and then the units, like I said, are a little bit tricky on this type. Sorry, that kind of took forever for me to erase. Alright, and so again, let's try this one. So try it on your own, check those units. Alright, and let's look at it together. So it says a power tool uses about 12 amps of current. So there's my I. And has a power rating of 1,440 watts. So there's my P. What voltage does it require? So we're looking for V this time. So again, we're going to have to rearrange. So power is current times voltage, but I want to solve for V. I want to solve for voltage. So we have to get I onto the other side. So right now we're multiplying, so how do we get to the other side? We do the opposite. The opposite of multiplying is dividing. So V equals P divided by I. And so then I just plug in. So my power is 1,440 watts. My current is 12 amps. So when I do 1440 divided by 12, I get 120. And what's our unit for V or voltage? Well, it's volts, which is V. That's the easiest one to remember. V is V. All right, so hopefully you got that one right. If not, there's still a couple more to try in this video. So, electrical safety. Correct wiring, fuses, circuit breakers, insulation, and grounded plugs can help make electrical energy safe to use. Because the problem is, we can be electrocuted. Electricity can start fires. So how do we make it safe? These are some of the ways. So a fuse prevents current overload in a circuit. So if you plug too many items in to the same outlet, overheating can occur. So a fuse is there to help break the circuit if it does start to overheat. A circuit breaker, which is what we use more often than fuses at this point, a circuit breaker is a switch that opens when current in a circuit is too high. So you probably have something that looks a little bit like this in like your laundry room or maybe your basement or your garage. And so what will happen is if too much current is passing through a circuit, it will switch off. And then everything in that part of the house goes off. And so then when you realize like, oh gosh, my lights aren't working, you go outside, you try to figure out what the problem is, correct it, and then you can flip it right back on again. The transfer of excess charge through a conductor to earth is called grounding. So if you've ever seen the 3-prong outlets, the plugs, instead of just the 2, it has that third one, that is your grounded plug. Or sometimes if you're putting in a light fixture or something, you'll have an extra wire that you screw into really nothing, and that's your grounding wire. And so if there is an excess buildup of energy or charge, it can just pass through that instead of necessarily electrocuting like a person or something like that. So, section assessment. Name 2 elements included in a circuit diagram. Well, we talked about lights. You gotta have a wire. You can have your source like a battery. You can have a light bulb. You can have a resistor. Any of those things. A fuse, a switch, any of those. Just pick which 2 you like the best. What's the difference between a series circuit and a parallel circuit? A series circuit has one path. A parallel circuit has multiple paths that the charge can flow through. Okay, so a series circuit has one path, a parallel circuit has multiple paths. Write the equation for calculating electrical power. Well, power equals current times voltage, or you could write P equals I times V. That's the easiest way to write it. P equals I times V. Name 5 safety devices used with electric current. Well, we literally just listed those. So you have correct wiring, you have insulation, you have grounding, you have fuses, and you have circuit breakers. Okay, it's really on the side right before this. It lists all 5 of them. You plug in a string of holiday lights and notice that the entire string turns off if you remove one bulb. Explain why this happens. Well, if you remove one bulb and all of them go out, what type of circuit does it have to be? Well, series only has one path. So if one thing goes out, all of it goes out. So the explanation would be it is a series circuit. Okay, so you have to have all the light bulbs working for any of them to work. So the explanation is it's a series circuit. Alright, so if you didn't get any of those math problems right now, you got 2 more chances. Okay, so pause the video, try it on your own, and we'll look at it together. So a stereo receiver uses a current of 2.2 amps, so there's my I, from a 120 volt line. So there's my voltage. What is its power? So we're looking for P. So P equals I times V. Since we're solving for P, I don't have to rearrange, I just plug in. So my I is 2.2 amps. My V is 120 volts. And so once I multiply, I got 264. And our unit for power, of course, is watts. All right, so hopefully you got that one right. Okay, again, pause it, try this one, and then we'll look at it together. So a television connected to a 120 volt line, so there's my voltage, uses 102 watts of power. So there's my power. How much current flows through it? So I'm looking for current, which is I. So I'm going to have to rearrange that formula. So P equals I times V. I want to solve for I, which means I needs to be by itself. So how do I get V on the other side? Well, I do the opposite. Right now, I and V are multiplied by each other. So what's the opposite of multiplying? Dividing. So I divide both sides by V. So I equals P over V. And so I just plug in. So my power is 102 watts. My voltage is 120 volts. And so once I do 102 divided by 120, I get 0.85. And what's my unit for current? It is amps, or capital A. Alright, so hopefully you got at least one of those right, if not both of them. But remember, it's very important you be able to rearrange a formula in physical science, because we don't just use the formula the way it is all the time. A lot of times we'll rearrange it. Alright, so hopefully you understand a little bit more about electrical power, the difference in series and parallel circuits, and how to calculate power.